Okay, so chapter 13, we started off with some of the holdover material from chapter 11, or that things that we had covered in chapter 11 and 13 were both in the same thing. And the first thing we talked about was intermolecular forces. You need to know all four. You should know their relative strengths. Oops, hydrogen bond, not homework. So you should know their strengths, and I, of course, ranked them from lowest to highest. I don't know which way it matters. You should be able to tell me a brief statement about what they are, covering the important points. Meaning, you need to know that all molecules have London dispersion and it's proportional to size. You need to know that for a dipole-dipole, it needs to be an unsymmetric distribution of charge, and that when you draw it, you need pluses and minuses. For hydrogen bonding, it has to be hydrogen bonded to either oxygen, nitrogen, or fluorine. We should also point out for LDFs, those molecules are generally very symmetrical, or that the difference in electronegativity between the atoms is very small. And then ionic, it's between full plus and minus charges. And then you should be able to draw one example of each. An unsymmetrical distribution of charge, and it really should be asymmetrical. It's probably a better term than unsymmetrical, even though I guess both are the same. Then you should be able to draw one example. And so for LDF, it's important that the example is symmetrical and there's no partial positive or partial negative in it. Now that doesn't mean that if you draw this molecule, you know, that is an example of London dispersion forces. Why is that not a good example for London dispersion forces? Well, proportional in size simply means bigger molecules are more things. So you can draw a small molecule or a big molecule and they can have London dispersion forces.
I don't know.
It's not symmetrical.
Okay, that's what I said, but I was like, wait.
Meaning, if you draw it sort of trying to look at it 3 dimensions, you can put the chlorines more on one side than the other so that this side is partially positive and that side is partially negative. So this would be a good example for dipole-dipole, right? So what I'm saying is be careful of the molecule you pick. And then let's see. So a good example of that is anything that is mostly, you know, molecular compounds, CH4. And remember, CH4 means it can be C anything, right? As long as there's 4 of them and it's symmetrical. For dipole-dipole, be sure you include something that's unsymmetrical and then show the partial plus, the partial minuses.
So for LDFs, you don't do the partial plus?
That's the whole point. They are symmetrical, just there's no dipole-dipole interaction between them, so you can't draw the partial pluses and partial minuses.
Okay.
What are the partial pluses and minuses due to? Yeah, the unequal distribution of charge due to the differences in electronegativity of those atoms. And remember, the electronegativity is due to how much they want the electrons in those shared bonds. So what we're saying is that some of the bonds want the electrons more, so they get the electron a little bit more. It's kind of like maybe having partial custody of kids. If you have 70% and someone else has 30%, that's an uneven distribution, right, of the child. And so, you know, one parent could be considered partial positive and one parent would be considered partial negative. Let's see. Also be sure that you remember that this means sharing electrons, right? This is what we use to represent an intermolecular force, which is simply an electrostatic attraction between things. Let's see. The other thing to remember about dipole is don't show hydrogen bonds, meaning water is a horrible example for dipole-dipole, right? Because water is a good example of hydrogen bonding. For hydrogen bonding, it's basically the same as dipole-dipole, but you have to have oxygen bonded to either oxygen, nitrogen, or fluorine, not any other elements. For instance, this is a good molecule to illustrate dipole-dipole, or I'm sorry, hydrogen bonding interactions. It's one most of you are very familiar with. But where do I have to show the dipole-dipole interaction? Or I'm sorry, the hydrogen bond. Yeah, so this is what we call a hydrogen bond. It's between that and another oxygen on another molecule. What if I show this? What is this really illustrating? Yeah, this is mostly LDF, meaning this hydrogen right here isn't capable of forming a hydrogen bond. And so, yes, that molecule is attracted to other things, but it's not a hydrogen bond. And so hydrogen bond is specifically the hydrogens that are only bonded to the oxygen. And then for ionic, the key is to pick anything that has a positive and a negative charge. And don't do silly things like this, because what does that mean? Well, yeah, it's saying they gain, lose, and share. Not sure how you do that exactly. It might be possible, you know. So that's good and dandy if you want to memorize the definitions. But remember, memorization only gets you so far. I will, remember I'm taping this, I'll post this. If I go a little too fast, you guys have plenty of time to go and review that online. We do have 4 chapters. And it's a repeat of our lectures. Are we good to go, Oksana? So remember, it's applications that are important too. And so what are the applications of intermolecular forces? Where do we use them in these chapters that we've been discussing? Yeah, we can talk about vapor pressure, and that's proportional to those, or inversely proportional to those intermolecular forces, right? What about boiling point? That's directly proportional to those intermolecular forces, right? And we even use them when we're talking about solubility. And so I can ask the question that simply says, you know, define them and draw me them. And that's wonderful. It's a good question. But the applications are probably where you show me your true understanding. For example, if I show, say, 4 molecules, which one am I missing? And actually, why don't I just draw their Lewis structures, since really that's the first thing you should do. So see, I can ask questions like, for instance, order them from lowest to highest vapor pressure. In which case, which one has the lowest vapor pressure? And remember, they're opposite, right? So 1 is ionic. This is hydrogen bond. This is LDF. This is dipole-dipole for their most important intermolecular force. And so we should go 1, 2, 4, 3, right? For vapor pressure. But if I do boiling point, it's the exact opposite, right? It's 3, 4, 2, 1, or even melting point. They're the same difference, or heck, technically even freezing point. They're all a measure of the strength of the intermolecular forces. And then what if I talk about solubility in water, since that's what we're normally talking about? Which one's the most soluble in water? Probably number 1. And the reason for that is we know that K plus and Cl minus will certainly break apart and dissolve 100%. Now, you know, you can try to say certainly 1 and 2 are both going to be pretty soluble in each other, right? I think ammonia is probably 100% soluble in water, and KCl is pretty darn close, meaning you can almost put any amount. And so 1 and 2 are good answers. 1's probably a tiny bit better, maybe. So 1, 2, 4, and 3. So that one kind of corresponds to vapor pressure. What if I wanted to go from lowest to highest solubility in, say, ether? So ether is CH3-O-CH3. Actually, that's dimethyl ether, but that's okay. Solubility. And here, which molecule is most likely to be soluble in that one? It's dimethyl ether, technically, is the name of that, but the Lewis structure is kind of the way I have it drawn. Meaning, what intermolecular force is this capable of? And it's a very weak dipole-dipole, like very, very weak, because it's mostly symmetrical, right? It's only got that little oxygen in the middle that can form a dipole-dipole. And so, if we were to say this, it probably would be 3, 4, and it could be either one. Certainly, 2 and 1 are not going to be terribly soluble in it at all. So, the idea behind intermolecular forces is that they're used in a whole lot of different things. I'm probably forgetting some since I'm doing this off the top of my head. What else is it important for? Well, 4 can make a dipole-dipole interaction with water. So, since it can form a dipole interaction with water, it would be more soluble in water than something that cannot. Because remember, water forms hydrogen bonds, but hydrogen bonds are just a special, extra strong dipole-dipole, right? So, you know, every time you write hydrogen bond, you're really saying or implying that you've also got a dipole-dipole interaction there. It's just that if we're just listing the most important one, the strongest one there is the hydrogen bond.
In that example, the lowest to highest in solubility of that or whatever,
Yeah.
can that be also a hydrogen bond? Because H is O?
Well, there is no H right here, right? There's no hydrogen attached to that oxygen. Here?
That's what it's going on.
Yeah, but this is what it really looks like when you draw the Lewis structure, meaning you can't have the hydrogen stuck to the oxygen, because you can't have oxygen, hydrogen, something, right?
Well, we have our little boxes.
Yeah, if you really think you need the box, you certainly can pull it out. I'll go get them. I don't think you'll need them, but you always have access to them if you want them.
But like just even for me, it helps because looking at that drawn out, it looks symmetrical to me. But I understand my.
Which one looks symmetrical?
The fucking methylene one we just did when we just.
This?
Yeah.
Okay. I can see where it does look symmetrical, but then we have to remember that that's a bent.
Yeah. That's why it helps me.
Okay. No, that's fine. That's certainly you can have the model kits. I don't care. I would give them to you on the very first test, but they probably wouldn't help you. Meaning, you always have access to them. They're not. You can't really cheat with the molecular models terribly well. Let's see. The other thing in Chapter 13 that we moved on to was a heating diagram. So let's sketch one out. The key part is the shape is always the same, right? The only thing that technically will change is the two values that we plug in right here, right? So this is temperature, degrees Celsius, this is energy, kilojoules per mole, or whatever it ends up being, kilojoules per gram. You can plot it in any sort of energy units. What if I were to plot that for something that isn't water? For instance, on your cheat sheet, and I have to admit I printed off new copies of cheat sheets so you don't have it on your current version. But what if I said it was for, say, ethanol. And for ethanol, we know its boiling point is, I think, 78-ish and minus 116 degrees Celsius, something like that. I'm making it up. What does that mean I need to do for my chart? What does that mean I need to change? Yeah, see, this needs to be minus 116, right? And that needs to be 78 degrees Celsius. So remember, when you're drawing a phase diagram, don't get stuck in the fact that we always use water as our examples and 0 and 100 make sense, right? Always make sure that you're reading the problem and kind of focusing on it. For instance, if I ask you what phase change occurs when it goes from, say, minus 120 degrees Celsius to, say, even 20 degrees Celsius. Well, if it's, well, actually, here, let me pick another one too, minus 15 degrees Celsius. If that's water, is there a phase change between minus 20 and minus 15 for water? No, it's a solid, right? But if it's ethanol, is there a phase change? Yeah, solid to a liquid. And so that means, for instance, if I say how much energy is required to melt 100-gram snowball of ethanol and convert to steam, that's the exact same question with the exception of the word ethanol to say, for instance, if I had done water, right? Right. So what you have to realize is that it's the same process that we did, for instance, on the example in class. You know, we're starting here and we're ending here on our chart, right? So there's 1, 2, 3 steps, but the numbers you're sticking into that equation are different, right? That for that first step, that uses delta H of fusion for ethanol, right? Not water. And that second step, you know, when we're using Q equals M, that's supposed to be a Q. And for step 2, when we're using Q equals MS delta T, well, here we have to remember to use S for ethanol. And here, what's my change in temperature? It's actually 78 to minus 116, right? It's 78 minus a minus 116 degrees Celsius. You know, it's not 100 degrees Celsius. So one thing I noticed when I gave this out as a practice problem, people want to just default to using everything for water. But remember, all those values are specific to whatever compound we're talking about. And so if I give you a question about ethanol or I give you a question about some other substance, make sure you're using that other substance, right? Yes, Q equals MS delta T and Q equals M delta H of fusion. If you need those, they should be on the cheat sheet. Although you were supposed to memorize this.
Well, yeah, I got that one, but I don't.
Chapter 4. And, you know, if you really can't remember an equation, I'll tell you what it is. But those are things that, if you've been doing enough homework questions and practice, probably there. Yeah. But there was 3 questions on the homework on it. There was, tell me where you use it, define all the variables, and use it in a question. That should be. I'm not saying it's horrible. I'm just saying that in general, you know what's on the cheat sheet, and you know that if it's not on the cheat sheet, that reserves it for memorization, like the 10 acids. So you should know your 6 phase changes. Let's see, what else have we got here? And then the other thing that we had going on in this chapter was everything to know about vapor pressure. So what's vapor pressure independent of? Yeah, size of the container, the amount of liquid. What is vapor pressure dependent on? Yeah, which we said is really the intermolecular forces, meaning that's why the identity matters, right? Because it's different molecules have different intermolecular forces. What else is it dependent on? Yeah, temperature. And we know they even can put what the orders are. Vapor pressure is proportional to 1 over the intermolecular forces, or we call that inversely proportional. And vapor pressure should be proportional to temperature. At least you can say that that's directly. And I should point out that there is an option on the test, and there was an option on the practices for those people that have been coming to office hours and asking lots of questions. For instance, if I say vapor pressure and I leave a little line here and we say atmospheric pressure, and your choices are, of course, inversely, direct, or none. And should be none, right? Meaning the vapor pressure doesn't matter on the atmospheric pressure. Now, the relationship between vapor pressure and atmospheric pressure is simply when they're equal, something's boiling, right? But they don't depend on each other. If the atmospheric pressure increases, the vapor pressure doesn't increase to match it or decrease. It just is what it is. In fact, technically for vapor pressure, we usually are talking about an open or a closed container to really measure it. So remember that if it's not something that you know is related to each other, then none is an option. It's kind of a tricky option, I have to admit, but it is. What do we know about vapor pressure and boiling point? Yeah, something that has a high vapor pressure is going to have a correspondingly low vapor point. What do we know about, say, atmospheric pressure? So if something's inversely proportional, it means a high vapor pressure gives you a lower boiling point, and vice versa. What about atmospheric pressure and elevation? Well, let's see. If you go up, so you increase elevation, atmospheric pressure should decrease, and so that would be an example of inversely. And let's see, you know, we can keep doing these. What's the relationship between intermolecular forces and atmospheric pressure? Should be none. There's no relationship. The intermolecular forces holding together whatever liquid we're talking about have nothing to do with the atmospheric pressure, which is simply the weight of the entire atmosphere pushing down on us. So we can have all sorts of relationships like that. So if you take about every vocab word we've had, meaning every property we've talked about, let's see, how many of them can we list? Melting points, boiling points, freezing points. Let's see, what else did we have in there? Oh, intermolecular forces, solubility. What? Oh, I know they're the same thing, but, you know, it seems like it tricks people when they... Well, it seems like somehow if I talk about boiling points in class and then ask a question on freezing points or melting points, which arguably are the exact same value, it's just the direction you're going, that confuses people. So I'm listing them all out. Solubility, rate of dissolving. Heck, I can throw in random stuff like mass. Oh, we've got osmotic pressure. Let's see, we've got boiling point elevation. We've got freezing point depression, and we already said vapor pressure. So I mean, I can relate or ask you questions about any combination of those.
What was the boiling point? Which is an increase of boiling point, decrease of freezing.
Well, what causes the boiling point to increase? How can I increase the boiling point of a substance? There's two ways that I can think of. I can lower the atmospheric pressure, right? Well, that is, how can I well, yeah, I can lower the vapor pressure. So how do I lower the vapor pressure, though? Lower what?
What volume?
Increasing the atmospheric pressure.
Well, that doesn't change the vapor pressure. That will change the boiling point because it changes at what temperature the vapor pressure and the atmospheric pressure are the same, but it doesn't physically change the vapor pressure. So we already said that, right? Elevation, meaning atmospheric pressure, changing it. How else can I increase the boiling point? Think not chapter 13, think chapter 14, very last section in it. Whoops. These are all colligative properties, right? And so, for instance, I can simply increase the boiling point by increasing the number of moles of solute. Technically non-volatile since we use that word a bunch. So, but just by dumping a bunch of junk in my stuff, I can increase its boiling point, right? Now, I'd argue that it's much easier to just change the atmospheric pressure and get a pressure cooker or something than dumping a bunch of junk in it since it's a very small effect. But, you know, we can relate any of these quantities together, and if you have a really good understanding of the chapter, you should be able to kind of think about the relationship between them. And so one of the things maybe you need to have in the back of your mind is a good picture of what's occurring during any of these processes, right? So what's the picture that you have in your head for vapor pressure?
Decrease the boiling point to increase the number of moles.
To increase the boiling point.
To increase means
Right.
directly.
So this would be directly proportional if I'm trying to increase the boiling point. The more solute I have, the higher the boiling point. Taylor?
Wasn't there two things with dissolving? There was rate of dissolving and something.
Yeah, solubility, rate of dissolving.
Okay.
So what's your picture of vapor pressure? When I say vapor pressure, what do you picture other than the word VP?
That beaker with the damn bubbles.
Yeah. I mean, remember, vapor pressure is just the equilibrium between molecules in the gas phase and molecules in the liquid phase. And so if you have a picture of that, then you can maybe think about how that affects the solubility of gases or how that affects the solubility of liquids. Oh yeah, we forgot. We can also put pressure in this list. Let's see, I think that exhausts chapter 13. Chapter 14 was, let's see, and see, have you noticed that they kind of mix together? That there certainly is a chunk of overlap? That the trends that we talk about in chapter 13 extended into chapter 14? I would say chapter 14 again started off with intermolecular forces. We introduced the concept of solute, solvent, solution. We had words like miscible and immiscible. We had words like soluble and insoluble. Talked about unsaturated, saturated, supersaturated. Are all those words familiar to people? Okay, and again, it's not so much the definition, it's the usage, right? For instance, can you give me an example of something that's miscible? Let's take a step back. What does miscible mean? Yeah, two liquids that mix. Can you think of in the existence of your life two liquids that mix? Yeah, Neo and water is an example. What would be something that's immiscible, that does not mix? Water and oil. Meaning, remember, definitions are wonderful, applications and examples are superior, usually. I mean, don't get me wrong, you have to know the definition so you can use it properly. But if you can memorize the definition, that proves you memorize the definition. If you have examples in your head, that means you might be able to extend that definition to real-life applications. What does soluble and insoluble mean? Can you give me one example of something that's insoluble? What? Right, so usually we talk about something being soluble as a solid dissolved in a liquid. Can someone give me an example of a solid that, oops, yeah, dissolved in a liquid? Yeah, that's a good example. What about something that's insoluble? Yeah, so give me an example. Yeah, aluminum plus water. You have to be careful because, for instance, if you throw sodium in water, it dissolves just fine. Sodium in water, it dissolves just fine. And so when you say throw a metal in water, well, that's not true. There's plenty of metals that'll dissolve in water. There's plenty of metals that don't dissolve in water. So, you know, a specific example would probably be best. Heck, do you realize you have probably an entire chart of these, right? I could probably ask you to give me 50 examples and you should be able to do it, right? What is unsaturated, saturated, and supersaturated? Yeah, so less than, equal to, greater than the amount. Can you draw me a picture of those? What would an unsaturated solution look like? Unsaturated means there's more solid that can be dissolved, right? So if you have solid sitting around at the bottom, is that unsaturated? No. What about saturated? There should be extra solid, right? Meaning saturated means I've dissolved the maximum amount, and so you should be able to see a little bit of solid undissolved, right? Here's what's tricky. What does supersaturated look like? Should technically look clear. Remember, what's the trick about a supersaturated solution?
It's not gonna be a condition. It can be clear in high temperature and cool it off.
Right, it's unstable, right? So if you had a supersaturated solution, it might look clear, but the second you disturb it, the second you scratch the side of the beaker or something, you'll notice that all of it starts precipitating out. Or if you certainly cool the temperature. Like for instance, a supersaturated solution of Jell-O, if left alone, will eventually, you know, go from liquid to a solid. And people know that it's above the line, below the line, and on the above the line, below the line, and on the line, except not in that order. You get the graph on your table, or you'll notice in the new cheat sheet I gave you a small solubility table to use for questions.
Is it on the side?
What?
And then she's showing the side.
I just posted it this morning. But anything that you had access to a certain extent on your homework, aside from like literally having the book in front of you open, you would get. So if there was a graph that you had to consult on your homework, you would get that on a test or the equivalent. So think about the graphs that you got on your homework. You got your solubility table on your homework, right? Or that graph that showed all the solubilities, right? You also got the graph that showed the vapor pressure of what? Diethyl ether, ethanol, and water. So I mean, you get anything that you had to consult on homework, you should be able to do. Conversely, things that you didn't get on your homework that you had to draw, for instance, the phase diagram, you know, you wouldn't get that on a test, right?
I have a question about that. So the part, like where the line is flat,
Right.
the energy goes to just, that's like when it's heating up, right? And then
No, because the curved lines are where the temperature changes, right? Meaning,
so
if we look at these two processes, here, this is the change in temperature, because that might be 0 degrees Celsius, and that might be whatever temperature we're at. So here, there's a change in temperature, right? So this is increasing the kinetic energy of the molecules. Here, this is what we call a phase change. What we're really doing is we're essentially breaking, and maybe that's the wrong term, weakening. Before you came? Yeah. I'm taping the whole thing if you want to watch it. Weakening or breaking the intermolecular forces. Because there's no change in temperature. Jay Bradley, games tomorrow night at 7, right? A little sleepy. Did you guys get back late? What? Ridiculous. I guess it's better to be in class and tired than not in class at all, but still tough. Still tough. Oh. So, for solubility, unsaturated, saturated, supersaturated. The other thing you had to be able to do is, for instance, you need to be able to use ratios, right? So if I have 25 grams of X and 35 grams of water, what do I have to do? Yeah, I have to figure out and compare it to 100 grams of water over whatever value, and then compare it to the chart. And so you have to remember your cross multiplications. What if I ask a question, though, about how much will precipitate out of, say, a saturated solution of KCl at 50 degrees that is cooled to 30 degrees Celsius? Well, that's just a subtraction, right? Meaning you find the solubility at 50 degrees Celsius, which, oh, what the heck, we'll put some numbers in. KCl at 50 is about, say, 43 grams. And at 30 degrees Celsius, KCl, oh wait, I was looking at the wrong one, wasn't I? KCl at 40 is more like 39. Oops. Oh, I'm 43. I keep looking, and then KCl at, what did I say, 30 is about, say, 36. And so we would expect 7 grams to precipitate, right? And so, or I could reverse the question, right? And I could say, how much more can I dissolve going from 30 degrees Celsius to 50 degrees Celsius? Then it's the same question, right? Meaning it's just asking what's the difference between those lines. And if I'm cooling something, that's going to cause it to precipitate out. If I heat it, I can dissolve more in it, right? Yes, no, makes sense, not make sense? Bless you. Yep. And then we can combine those. Did you want me to slow down for a second? So if I heat something, then I can dissolve more, right? If I cool something, that means I precipitate out, right? Think about it like Jell-O. If I'm heating the Jell-O up, I can dissolve more Jell-O in it. If I'm cooling the Jell-O down, it's going to precipitate back out.
And if you're trying to find a dissolve, you still subtract.
Yeah, it's still the difference between those lines. It's simply a question of phrasing the question, right? And then you can combine the questions, for instance, and say, I have 25 grams of KCl in 85 grams of water at 50 degrees Celsius. How much can I either, well, I guess I could ask the question, is the solution unsaturated, saturated, or supersaturated? And then you can just simply say, if it's unsaturated, how much more can I dissolve? And if it's supersaturated, I can ask how much should precipitate out. And so we'd say 25 grams of KCl all over 85 grams of H2O is the same thing as 100 grams of H2O all over X. Solve for X and I get what? 25 times 100 divided by 85. That's 29.4 grams of KCl. And at 50 degrees Celsius, we said for KCl, what did we say? It was 43. So at 50 degrees Celsius, saturated equals 43 grams per 100 grams. So is my solution saturated, unsaturated, supersaturated? Yeah, it's unsaturated. And what that means is that I can have more dissolve. And so I can simply say, well, if it's supposed to have 43, and I only have 29.4, how much more can I dissolve? 43 minus 29.4, 13.6. Wow, we got some mathematical geniuses here. My brain's too tired. I've only had this much coffee, so.
So it would be the same.
Grams will dissolve, right? But that's assuming 100 grams, right? Is what the same answer? No, because it would have to be above the line, so that 29.4 would be some different number, right?
Then you would add.
I mean, it's the same process. Right. So I've got 13.6 grams. Well, that's 13.6 grams per 100 grams all over 85 to find out what I really would have. So 13.6 times 85 divided by 100 means 11.6 grams can be dissolved. So remember, you're always kind of going back and forth between what you really have, meaning I have something dissolved in 85 grams of water, right? And then I also have the chart that's in terms of 100 grams. And so you can either convert everything on the chart and do it, and then convert back, or you can convert all the information on the chart to 85 grams and do the problem. Meaning there's more than one way to skin this cat. I know. Every time we skin a cat, it makes things more confusing.
So the 11.6
This is the correct answer. Because see, that 13.6 would be if I had 100 grams of water, right? But I've only got it dissolved in 85, so I can't dissolve as much in it. What else was on 14A? Rates. So you should know that it increases with temperature. It is increases or decreases with particles. Wait. Okay, let's do this. So this is the rate of dissolving. And so rate is directly proportional to temperature, right? Meaning the more the it'll dissolve faster the higher the temperature, right? Rate compared to particle size is inversely proportional, meaning the smaller the particle, the faster the rate, right? But it's directly proportional to surface area. And so remember that particle size and surface area are inversely proportional, meaning big particles have very small surface area. Very small particles have large surface area. There's an entire class of compounds that are high surface area compounds. For instance, you can kind of think about it if you want as a biology example. How long is your frickin' intestines? 22 feet. You've got 22 feet of crap just curled up in your thing. Or what about DNA? Isn't DNA pretty darn amazing if you actually stretch it out, how much it curls up into a little ball? Like, I can't remember. If you took all the DNA in the human body, I don't remember the exact number. It like goes to the moon and back or something stupid like that, where it's just ridiculous how much DNA we have coiled up in us, right? And so it's the same thing. You know, small things have very large surface areas. Very large objects have very small surface areas comparatively. What are the other two? Stirring, right? Or we can argue that that really is simply kinetic energy. And then that's directly proportional. The faster I stir something, the faster it's going to dissolve in general. And then the last one is concentration. And that's inversely proportional, meaning the more concentrated the solution, the slower the remaining stuff dissolves. Of those, I think the first three are probably the most important ones. The last two are somewhat useful in real life in that, you know, we often stir things, but beyond that in chemistry, we don't worry about it too much. Let's see, what else do we got in chapter 14? Oh,
What's that last one?
concentration. Meaning if I've already got a lot of substance dissolved in something, the rest of it dissolves very slowly. So a little bit dissolves fast, a lot takes a long time to dissolve. We had concentration units, which primarily meant molarity. I'm not going to go beyond that because, well, you guys should know molarity by now. Because it's been in chapter 9, we used it in chapter 15, we used it in this chapter. Molarity is molarity. The one we should be aware of is M1 V1 equals M2 V2. How do I know when to use that equation? Well, for instance, if I have a question that's listed as 25.0 milliliters of 3.0 molar HCl reacts with 50 milliliters of NaOH. What is the molarity of the NaOH? Would I use M1 V1 equals M2 V2? So I've got two volumes and a molarity, but I don't use that equation. So it's not just having 3 out of the 4 parts. Yeah, it has to be the same molecule. Because if they're different, you're going to have a mole-to-mole ratio that you have to worry about. Meaning that this is a titration problem from chapter 15. So one of the things I mentioned yesterday in class, I thought, and I don't remember honestly, is that the information for a titration problem and the information for a dilution problem look the same, right? So there's key things that you have to pick up on. First off, this is the same molecule. Titrations are different molecules. This involves a chemical reaction. Well, an example of this would be if I took 25.0 milliliters of 3.0 molar HCl and diluted it to 50 milliliters. Oops. What is the molarity of HCl? Notice that here I'm only talking about HCl. In the previous question, I'd talk about HCl and sodium hydroxide. So notice that this usually will have the magical word dilution in there. Not always, but a lot of times it'll have dilution. This will usually have the magic word titration, or more often neutralization. Now I can't guarantee that, meaning sort of when I write my tests, I usually do put those words in because I remember to do it. But you know, if you were in another textbook in another class, who knows if they would make sure to use those words or not, if they were to just simply be implied.
So it's more important to remember that it's the same molecule as it.
I would say that's the better choice. And just think about the process. If a chemical reaction is occurring, M1 V1 equals M2 V2 is not appropriate. If there's no chemical reaction and you're simply adding or removing water from something, then that really is just diluting the sample, meaning changing the concentration of it. So you can also think about it as, you know, the fact that the chemical reaction has to occur there. That's 14B. Jess?
Does it matter which side of that you use? Like if I would put
Now, I usually do the concentrated side and then the dilute side. But that's just me, meaning no, it doesn't matter. But I like to be consistent in anything I do. That way when something funky happens, and it doesn't match my expectations, then I'll know what to do. Like for instance, if you always have concentrated and diluted, this should be the large volume and a small molarity, right? And so, you know, I can kind of realize that, hey, I diluted something and my molarity got more concentrated. Nah, I must have done the math wrong. Or I diluted something and my volume didn't get bigger. Must have done the math wrong. Meaning, you know, I can apply a little bit of common sense if I kind of do the same process over and over again. It's one thing you guys should also recognize. I mean, half the time, you know, if you get an answer that doesn't sound like it makes sense, then look and see what you did wrong potentially. Meaning if I'm reacting an acid and a base and I have a little amount of acid and I have a very strong base and it seems like I need 10,000 milliliters, I probably made a mistake. You know, you can kind of use some guesstimates like that.
Can I ask?
You can ask whatever you want, Oksana.
So in this last problem for today's homework, I could use the M1V1.
No. That has to be a chemical reaction. At least if I'm remembering the homework right, there is no M1V1, M2V.
Oh, 15D.
Okay, the last part of 14 was colligative properties. Well, that's where we use molality, right? So colligative properties are basically saying that as the number of moles increases, we know some things about vapor pressure, boiling point, freezing point, and osmotic pressure. So as the number of moles of solute increase, what happens to the vapor pressure? Decreases. I guess actually we should be saying it this way. It's inversely proportional, right? Boiling point is directly proportional. Freezing point is inversely proportional, meaning the higher the number of moles, the lower the freezing point, and osmotic pressure, capital O, capital P is what we've decided, is directly proportional, meaning the more moles of solute, the higher the osmotic pressure. And we said that the formula for these two are that the change in temperature for either one is equal to just mK, where this could be either temperature for the boiling point and K for the boiling point, or that we have the exact same formula for that. And so what we really realized is that when we're looking at sort of colligative properties, that little m is what controls things. That's moles of solute all over kilograms of solvent. And so if we want to know which one is going to cause the vapor pressure to decrease the most, we simply have to calculate the molality, right? If we want to know what's going to increase the osmotic pressure the most, simply calculate the osmology, the molality, and you know, whichever one has the bigger molality, it's going to have the larger property. Now for boiling point and freezing point, we can actually calculate the exact change because we can look up Kb and Kf, right? These are just constants. Now they're on the cheat sheet and they're solvent specific, right? Meaning if I do a problem in water, that's going to give me a different answer than if I do a problem in benzene or naphthalene or whatever else is on that cheat sheet. And so moles of solute is often needing a molecular weight to get to it. Kilograms of solvent is almost always just a metric conversion, right? And then the other thing to remember is that that delta T part is the change in temperature, right? And what that implies is that the temperature of the impure solution is equal to the temperature of the pure solution plus or minus that change. Plus if it's a boiling point because it gets bigger, right? Minus if it's a freezing point because it gets smaller. And so you have to be careful. If the question says calculate the change in freezing point, give me delta T, right? And if the equation says what is the new freezing point, then you have to add or subtract something. Nasty cold coffee. Let's see. That brings us to chapter 15. And hopefully most of this stuff you're just checking off in the back of your head that this is something you know. I'm just trying to point out sometimes the important processes, and I'm also trying to point out some of the things that people tend to get confused on. What do we need to know about chapter 15? We've got 3 definitions of acid and base. We need to know the definitions of strong electrolyte, weak electrolyte, and non-electrolyte. And we have to be able to apply them. And that's probably the biggest part right there, in that if we're trying to write a molecular equation versus a net or total ionic versus a net ionic, non-electrolyte. And what does this term electrolyte simply mean?
Do they break into ions?
Well, it technically means it conducts electricity or it doesn't. But we talked about the reason it conducts electricity is because it either breaks apart or it doesn't, right? This breaks 100% into ions. This only breaks 10%. And this doesn't, it has 0% as ions. And so what that means is that if I write HCl, aqueous, what I really have in solution is H plus ions plus chlorine minus ions, meaning that's how I really should write them when I write the total ionic equation. If I take something like a weak acid, so this is a strong acid, this is a weak acid, it means that when I write it in solution, I should leave it as HF because 90% of the molecules are actually molecules, only about 10% of them break apart into the ions. And if I have something like, say, CO2 gas, then I should leave it as CO2 gas because it doesn't break apart either. Now remember, just because something is a weak electrolyte or a non-electrolyte, that doesn't mean it can't be aqueous, right? It simply means that it doesn't break apart into ions. So, you know, C6H12O6 can be aqueous. It can dissolve in water. It can be floating around. That's just sugar. We know that dissolves. But we would write it like that. Whereas NaCl, now, if we're writing it out, we really should say, well, I know that NaCl breaks apart into sodium ions and chlorine ions because it's ionic.
So weak stuff we leave alone,
Weak stuff we leave alone, and non-electrolytes leave alone. And it's only the strong electrolytes that you have to break up into lots of little ions, because that's what they really are when they're dissolved in water. And so remember that. That's the key behind the total ionic equation, is it's supposed to represent the solution in water better. And then the net ionic equation is simply things that change, or things that react. And so we get rid of everything in the reaction that doesn't make any sense. Or I shouldn't say doesn't make any sense. Doesn't react. Doesn't change. Owen, drive safe. Oh, let's see. What else is in chapter 15? Oh, yeah, this little thing. Now I know, for instance, yesterday afternoon when we were going through these reactions, I had 4 different people asking me the same 4 questions. And so if you have questions on this, set up some time to ask them, because I tried to address it in front of the entire class, but those 4 people just decided to not pay attention. So, and I didn't feel like, and so if I'm going to answer questions individually, I'll be in my office. If I'm answering group questions, I'll be out here. I think that's fair. Let's see. We need to know, you don't get this chart. What you do get is a list of the equations, meaning pH equals minus the log of the H plus concentration. POH equals minus the log of the OH minus, you get that the concentration of H plus equals 10 to the minus pH. Concentration of OH minus equals 10 to the minus POH. That H plus times OH minus equals 1 times 10 to the minus 14 molar. And that pH plus POH equals 14. So you get these 6 equations. I'm not going to make you memorize them. What you do have to do is know how to use them on your calculator. And you do have to realize that if I have questions, sort of which direction or which equations I use. Meaning that, and actually maybe I should draw this differently. We should actually maybe draw it like this. Meaning that, for instance, between pH and POH, you have to use equation 6 no matter which direction you're going. And between H plus and OH minus, you have to use equation 5 no matter which direction you're going. But pH to H plus means, and actually, let me redo this. I want to be consistent. I always draw the top arrow going this way normally, and the bottom arrow going the opposite way. So pH to H plus means that I'm given the pH and I want to find the H plus. That means I need to use equation 3. Whereas if I'm given H plus and I want to find the pH, I need to use equation 1. And if I'm going from POH to OH minus, this is equation 4. And this is equation 2. And then if I want to go, for instance, between these two, this is 2 steps, right? Or if I want to go across from pH to concentration OH minus, that's again 2 steps, meaning that I can't convert directly from pH to concentration of OH minus. There's no single formula that does that. I have to use a combination of them. Jess?
With equation 6, how do you use it? Just add 14?
Well, they just add together. So for instance, if I said the pH equals 9, what is POH? It's just 9 plus POH equals 14. Yeah. And then also remember that anything that is a concentration has units of molarity. But anything that's a pH and a POH is unitless. I always think that's weird that somehow it's unitless. It seems like there should be a unit because everything else in chemistry has units, but if you take the log of something, it doesn't really have a unit. It's not a physical measurement. So that's also one of the silly things. For instance, you guys don't have to worry about it because we don't do serious acid-base calculations in this class. In Chem 111, it's funny because you always report things as pH and POH, and every single calculation you use H plus and the concentration of OH minus. So you're constantly converting back and forth between the two simply because that's what people do. It's kind of like in a chemical reaction, we're constantly converting between grams and moles so we can use our mole-to-mole ratio, right? It would be easier if we just wrote everything out in terms of moles in our reactions maybe instead of grams. But it's easy to measure out grams, it's hard to measure moles, so you constantly are going back and forth. Let's see, what else is in chapter 15? Oh, titrations, but we kind of covered that already. Oh, there's the definitions. I mean, we kind of mentioned that. And you have to tell me whether something's an acid or a base based on whether it's below or above pH 7. With, of course, the third option being neutral, right? And again, I'm covering the highlights, not every single question that could be on the test. Mostly because I haven't finished writing the damn test, so who knows what I'll come up with
Well, if you need help.
when I get creative.
So I have a question.
Aaron.
Do you have extra copies of like past tests that we've already taken?
Yeah.
Can you get a copy, or can I get a copy of yours?
Did you, so you can start practicing for the final?
Yeah, no, I get copies.
Sure, I tell you what, I'll post last year's, or post all the tests from this year up on the internet. I'm not going to post the answer key, but hopefully your test is mostly an answer key, and if your test is atrocious, then you should work hard at it. Did I just accidentally close everything out and not save my file for the review?
Undo.
Oh no, I haven't stopped.